Hi, welcome to your MECH 200 Statics online classes. Today we're going to start Chapter 2. This is the first of a series of 3 videos in which we are going to review a little bit of the math behind operations with vectors. This is very important to solve statics problems involving forces and displacements. I hope you enjoyed this video. Let's start by highlighting the main objectives of this chapter. First, we are going to review how to add force vectors and resolve them into components using what we call as the parallelogram law. Next, we'll learn how to express force and positions in the Cartesian form and explain how to determine the vector's magnitude and direction. And finally, we'll be introduced to the dot product of two vectors in order to use it to find the angle between two vectors or the projection of one vector onto another. We should start by providing at first a proper definition of scalars and vectors, which are the two mathematical entities that we use to measure all physical quantities in mechanics. A scalar is any positive or negative physical quantity that can be completely specified by its magnitude. Examples of scalar quantities include the length, the mass, and the time. A vector, on the other hand, is any physical quantity that requires both a magnitude and a direction for its complete description. Examples of vector quantities are the force, position of a particle, and the moment. A vector is graphically represented by an arrow. The length of the arrow represents the magnitude of the vector, and the angle theta between the vector and a fixed axis defines the direction of its line of action. And the head or tip of the arrow indicates the sense of the vector direction. In the print form, vector quantities are represented by bold-faced letters, and the magnitude of a vector is represented by a letter in italics. For handwritten work, it's often convenient to denote a vector quantity by simply drawing an arrow above the letter. After defining what scalars and vectors are, let's talk about some of the most common operations with vectors. And we should start with the simplest ones, which are the multiplication and division of a vector by a scalar. If we have a vector A, and we want to multiply it by a positive scalar 2, then the resulting vector will have its magnitude defined by that amount, in this case 2a, which means that the magnitude of the original vector was doubled, keeping the direction and sense unchanged. Let's take another example. If we have the same vector a, but now we want to multiply it by minus 0.5, which is the same as dividing it by 2, then the result will be minus 0.5a, which cut the magnitude of the original vector by half, keeping the direction unchanged, but changed the sense of the vector. It's important to note here that every time that we multiply or divide a vector by a negative scalar, it will always change the directional sense of the resulting vector. Now, let's consider the addition of two vectors. When adding two vectors together, it's important to account for both their magnitudes and directions. For this, we have to use the parallelogram law of addition. To illustrate this law, let's imagine that we have a vector A, and we want to add it to a vector B. First, we have to join the tails of the two vectors at a point to make them concurrent. Then, from the head of vector B, we draw a line parallel to vector A, and another line from the head of vector A that is parallel to vector B. These two lines intersect at a point P to form the adjacent sides of a parallelogram. Then, the diagonal of this parallelogram that extends to the point P forms a vector R, which then represents the resultant vector of the sum of A and B. Another way to add two vectors is using the triangle rule, which is a special case of the parallelogram law. Let's take the same vectors A and B. In order to add them using the triangle rule, we have to connect the head of vector A to the tail of vector B, and then the resultant force, vector R, extends from the tail of A to the head of B. It's also important to mention here that the addition of two vectors is commutative, which means that it doesn't matter if I add A to B or B to A. The result will always be the same. As a special case of the addition of vectors, if we have two vectors A and B that are collinear, which means that they both are oriented along the same direction, the addition is reduced to a simple algebraic or scalar sum of A and B. Now, let's see how to do a vector subtraction. It works in a very similar way of the addition. In fact, it is considered as a special case of the addition operation. Let's take once again the case of the two vectors A and B, and then we want to subtract B from A. Then, the resultant vector can be defined as the sum between vector A and negative B, which has its sense inverted for this operation. Graphically, we can show this subtraction by applying the parallelogram law for vectors A and minus B, and the triangle rule for vectors A and minus B. In both cases, the result will be the same. If we want to subtract vector A from vector B, then we just do the other way around, by taking the inverted vector A and summing to the vector B. Now, let's turn our attention to some practical application of the addition of force vectors. One common problem in statics involves finding the resultant force when its components are known, just like the forces acting in the hook shown in this figure. The calculation of the resultant force Fr will involve the parallelogram law according to the two components F1 and F2. Let's see how it works. In order to find the resultant force, first we need to redraw a half portion of the parallelogram to illustrate the triangular head-to-tail addition of the vectors F1 and F2. Remember that this is essentially the application of the triangle rule. Next, we have to mark the three internal angles of the triangle. Then, all we have to do is to play a little bit with trigonometry. If we take the cosine of the angle C and the magnitudes of F1 and F2, we find the magnitude of the resultant force through the cosine law. If we consider the sine of this angle and apply the sine law, we find the other two angles that define the direction of the resultant force. The next application involves situations in which it is necessary to resolve a force into two components in order to study its effects in two specific directions. Let's consider the example in which a force F is to be resolved into two components along two members defined by the axes U and V. In order to determine the magnitude of each component, a parallelogram needs to be constructed first by drawing a line starting from the tip of vector F parallel to axis U and intersecting axis V, and another line from the tip of vector F parallel to axis V intersecting axis U. The two force components, Fu and Fv, are then established by simply joining the tail of F to the intersection points in the U and V axis. Finally, this parallelogram can then be reduced to a triangle, which represents a triangle rule, and the sine law can then be applied to determine the magnitudes of the components Fu and Fv. Another very common application involves situations in which more than two forces are to be added, Like in this example here, in which we have three forces acting in the hook, and we need to calculate the resultant. We can do this first by adding F1 and F2 using the parallelogram law, and then taking this result and adding to F3, which will give us the resultant force Fr. Mathematically, this is the representation of the sum of the three vectors. Using the parallelogram law to add more than two vectors, as shown here, often requires extensive geometric and trigonometric calculations to determine the magnitude and direction of the resultant force. Problems of this type can be easily solved by using the rectangular component method, which will be explained in the next video. Before we show some examples, it's important to freeze the following points. The first point is that a scalar is a positive or negative simple number, which is essentially different from a vector, which is a quantity that has a magnitude, direction, and sense. The next important point is that the multiplication or division of a vector by a scalar will change the magnitude of the vector. Additionally, the sense of the vector will change if the scalar is negative. And as a special case, if the vectors are collinear, the resultant is formed by an algebraic or scalar addition. Now, let me show you one example on how we solve vector calculation problems. In example 2.1, we have a screw eye subjected to two forces F1 and F2, in which the magnitudes and direction of both forces were given, and we are required to determine the magnitude and direction of the resultant force. The best way to solve this problem is through the parallelogram law, by drawing a line from the head of F1 that is parallel to F2, and another line from the head of F2 that is parallel to F1. The resultant force Fr extends to where these lines intersect at point A. With that, we are ready to determine the two unknowns, which are the magnitude and the direction of the resultant force. Before we proceed with the calculation of the force, it's convenient to use this figure to determine the angles that we need to use in the sine and cosine laws. For that, we just need to apply some simple trigonometric relationships to the parallelogram shown here. First, based on the two angles given in the problem statement, we can easily calculate this internal angle of the parallelogram by subtracting the sum of 10 and 15 degrees from 90 degrees, which results to 65 degrees. With this information, we know from basic geometry that two pairs of opposite angles are equal in measure for a parallelogram. And then this angle here has to be 65 degrees as well. Finally, since we also know that the sum of the internal angles in a parallelogram must be 360 degrees, we can calculate those two angles here using this formula, which will result in 115 degrees for each. The calculation of this angle is very important, since this is the C angle opposed to the resultant force that we need to calculate its magnitude using the cosine law. Now, from the parallelogram, we construct a triangle with the two force components, the resultant force, and the angles theta and phi. Those two angles will play an important role on the characterization of the direction of the resultant force. Then the next step is the calculation of the magnitude of the resultant force using the cosine law. For that, we have everything we need: the magnitudes of F1 and F2 and the angle C, which is 115 degrees. And by applying those values to the equation, the answer is 213 newtons. Then next, we have to calculate the value of the internal angle theta by applying the sine law. In order to do so, we just need to take the magnitude of the force F2, the angle C, and the magnitude of the resultant force that we just calculated. After plugging all those values in the sine law equation, the result for theta is 39.8 degrees. However, a better way to characterize the direction of the resultant force is through its inclination from the horizontal axis, which is represented here by this angle phi. This angle is then calculated by simply adding 15 degrees to the angle theta, and the result is 54.8 degrees. We should check if the answers we just got seem reasonable by looking at the triangle figure. The magnitude of the force seems to be reasonable, since it is larger than the magnitudes of F1 and F2. The direction angle phi also looks reasonable, because according to the figure, the value for this angle is expected to be in between the values for the direction angles of F1 and F2 when taken from the same horizontal axis. With the previous example, you are now ready to study examples 2.2, 2.3, and 2.4 of the textbook on your own. Try to fully understand all steps involved in their solutions before you start solving the practice problems of this chapter. And that's the end of the first video on chapter 2. Thanks for watching, and I'll see you in the next video.